Okay, so we're going to start with a review question on current. So it says here a wire has a current of 4 microamps, remember micro having a prefix to it, flowing through it for a time of 10 seconds. So let's remember the formulas. I plus delta Q over T. Now the first question says how many coulombs of charge are flowing through it. So SI units for charge rather is coulombs, so we're good here. I was given this, and I was given this, so it's a pretty straightforward question. We got 4 microcoulombs, which is 4 times 10 to the negative 6 coulombs. We're looking for the charge, and we're told 10 seconds. So I do a little bit of algebra here, which I will give you guys a second to work on your own. And I'll get rid of that. We're going to say that the change in charge, or the charge that went through, ends up being 4 times 10 to the negative 5 coulombs. No. Okay. Now, the next one's a little bit trickier, but it just goes back to the very beginning of the chapter. So it says how many elementary charges are flowing through. So I already know how much charge flowed through in coulombs, which is 4 times 10 to the negative 5 coulombs. Now, we should remember that there's a conversion factor for this, so we can set up a proportion. We could say 4 times 10 to the negative 5 coulombs over, well, we don't know how many elementary charges, but we know that 1 coulomb of charge is equal to, still getting used to this computer stylus, 6.25 times 10 to the 18th elementary charges. You're going to cross multiply, and ultimately you're going to end up with a charge, in terms of elementary charges, of, I'll give you a second or two. Well, I'm giving you that time. I'll erase this so maybe I can give myself a little bit more room. We got a charge of 25 times 10 to the 13th E. Or, if you want to put it in proper scientific notation, 2.5 times 10 to the 14th E. So that basically just recaps what we did before the last week off. Now, what we're going to talk about today is we're going to talk about resistance. Now, I'll read this for you. It says, resistance is just the slowing of the current flowing through an object due to the intrinsic properties of the material. So we've talked about that term intrinsic already. It's just the properties that make the material that material. So whether it's a fat wire or skinny wire, whether it's metal or plastic, whether it's long or short, things of that nature. It's the actual physical properties of the wire. Now, things you absolutely need to know. The unit for resistance is the ohm, which is this weird looking Greek letter, which if you draw it bigger, it's kind of like a horseshoe. But that's obviously a better picture of it. And resistance is, in fact, a scalar quantity. Something either has it or it doesn't. Okay? So, let's look at this diagram. So there are 2 different ways we can look at resistance. The first one we're going to look at is based on the physical makeup or the physical characteristics of the object. So this drawing here actually is a really nice drawing, and it shows you all the pieces that build our formula. So here's our formula. It's R equals the Greek letter rho. We've seen this before for momentum, but this is not momentum, obviously. This stands for the resistivity, which is written up here, and it's written here. Now the unit for resistivity is an ohm meter, which we'll explain in a minute why that's the case. Okay? This is just length, so that's the length of the piece of wire, the resistor in question, so that could be in just meters. And A is the cross-sectional area. So that's if you were to cut it like that, it's the cross-sectional area there, which is shown in the picture, which they probably did a better job than me. So let's just clean up the picture. Now, the cross-sectional area is going to be in square meters. So if we look at R, rho L over A, R is supposed to be in just ohms. Resistance, or resistivity rather, we said is ohm meters. Length is meters, and area is meters squared. So unit analysis tells us that meters times meters is meters squared, and that goes away with meters squared, and that's why resistivity has a weird unit of ohm meters. Now, on your reference table, there is a chart. There's a chart of different resistivities of different metals. Okay, now there's a chart of resistivities for metals because those are typically the materials that are making up our electrical devices. So copper, we're obviously very familiar with that being in our electrical devices. If you have any high-end electrical devices, a lot of times they're at least coated in gold because gold's a pretty good resistor. It makes for a pretty good conductor, rather. Nichrome is a little bit cheaper, but if you notice, this is not a typo right here. That is 150 times 10 to the negative 8. So this is much, much bigger than all the other ones. Okay, silver, tungsten, aluminum, copper, gold. Okay, now, another thing I want to bring to your attention. This idea here. Resistivity at 20 degrees Celsius. Temperature is directly related to resistivity. Which means as one goes up, the other goes up. And as one goes down, the other goes down. Now, simple way of explaining this would be if I have an electron here and it's trying to get from point A to point B in a wire, and all these other molecules are in here, like this. And we remember, hopefully from chemistry, that temperature is the average kinetic energy of the molecules moving back and forth. The hotter this is, the faster these molecules are moving back and forth, like this. Which would make it far harder for this guy to get from point A to point B, which would mean more resistance. If this is colder, these things are going to be moving slower, and it would make it much easier for this guy, again, to get from point A to point B. So, temperature, directly related to resistivity. There are some materials out there that that's not the case for. For instance, there's something known as a superconductor. Now, superconductors are super cool, forgive the pun. They are materials that seem to obey this temperature versus resistivity thing. But right as it gets towards the end, we're talking about 50 degrees Kelvin, so super duper cold, all of a sudden, resistivity just drops off. And it goes to a resistance of 0 before a temperature of 0. So this is hugely important, because if we can figure this out, that's going to figure out the energy crisis. Problem is, as of now, this temperature requires more energy than we can possibly create on a large scale in order to get this so that we can transfer the energy. So if you guys can figure that out, well, just remember who your high school physics teacher was and send him lots of money. Now, moving on. We have this question here, which is going to be based on that formula that we just did. So there's a wire made of copper, 20 degrees Celsius. So this is one of those bells and whistles situations where you have to remember that term as soon as they say the material, and specifically the material at 20 degrees Celsius. That's going to bring us back to this guy, which we'll clear off now. So if we look, we have copper at 20 degrees Celsius. So we have a resistivity of 1.72 times 10 to the negative 8, again, ohm meters. So we'll go back. Nope, not too far. So we're looking for R. We know the resistivity, we just found it. We have the length, which is 2 meters, check. And we have the cross-sectional area, which, because I just started working with this program on an iPad, I don't 100% know how to write times 10 to the negative 6 yet, so we just did it old school. But we have the cross-sectional area. Check. So we're going to plug in our numbers. We got 1.72 times 10 to the negative 8 ohm meters times 2 meters all over 2 times 10 to the negative 6 meters squared. Okay, so I'll give you a second or two to do that math. We're getting ready to. I'm just writing this out because we know it's going to be R equals something ohms. Change it up a little bit. So that 2 can go away with that 2 and give us 1. So now 1.72 divided by 1 is just 1.72 times 10 to the negative 8 divided by 10 to the negative 6. We subtract the exponents, which ends up giving us 10 to the negative 2. So 1.72 times 10 to the negative 2 ohms. Simple enough. Now, I mentioned at the top of this that there was 2 different ways of looking at this. So the other way is kind of neat because it brings in all the other things we've talked about. It brings into electric potential, it brings in current, and obviously resistance. Now, this is probably the more user-friendly version we're going to get very, very used to using over the next, 2 to 3 weeks or so of our classes. So, this is what's on your reference table. This is the way we're going to do it. Okay. Now, very simply, if you look at this, this is saying the electric potential, or the amount of energy each individual particle has, is equal to the product of the current and resistance. So, hear me out. Let's say I have 10 volts. That means each little particle has 10 joules per coulomb of energy, let's say. Okay? So, the bigger my resistance, the bigger my friction, if you will, to stop it, the bigger the intrinsic want for this wire to stop that current from flowing, the smaller the current will be. The bigger the stopping power, the smaller the actual flow of current, based on that much energy. Seems a little bit more, convoluted right now, but I assure you, we will work a lot with this, and you guys will get very, very good with it. So, let's just do a real quick example question. So, the current is 4 microcoulombs, so 4 times 10 to negative 6 coulombs. Flows through a potential difference, V, of 100 volts. And the question is, what is the resistance? Well, you say V equals IR. So V was 100 volts. I is 4 times 10 to the negative 6 coulombs. We're looking for R. So we do some algebra. And again, I'll give you guys a second or two to figure that out. and should come out to be 2.5 times 10 to the 5th ohms. Just a really good size resistance there. So that's that for resistance. So just to recap, we talked about the two different ways of doing resistance. We have the physical characteristics way of doing it. So we have R equals rho L over A. That's kind of a hands-on way of looking at it. And then there's also this guy, which relates it to all the other things. This one will ultimately be more important to us because this is going to lead us into the next thing we do, which is circuits. Dum, dum, dum. I'm just kidding. It's actually not that bad. We're going to spend a lot of time on it since we have obviously nothing but time. So that's that. So my last little bit I want to talk about then is not necessarily about this lesson, but just things that we're going to note as we're moving on. So this is a new format, so I assure you it will get better. Obviously, this was probably not the best lesson you've ever seen me give, because I know I've given some fantastic lessons before. But just know that as I learn all the little bells and whistles and tricks for this, I will try to make our lessons better and more interactive. Okay, next one. Because we're not doing classwork as we traditionally would do in class, there's going to be about 10 or 15 or 20 minutes of me talking most of the time, and then I really need you to kind of do more than you might want to at home. I know it's going to be kind of hard. You know, your couch is going to be calling, things of that nature, but I really need you to be on top of your assignments because I'm not going to be in class with you kind of browbeating you into doing this. Okay? Now, this one I think will be very important for some of you because I know a lot of you guys probably miss my face. Just kidding. But we will be having a weekly face-to-face class on Zoom. I will be sending out more information about this later in the week, specifically like how you sign up for the Zoom, what time we're going to do it, what day we're going to do it. This week we'll probably be trying for Friday. Oh, that's not it. Why? That's next. Okay, Friday. And I believe I have you guys set for 10:30. Nah, don't quote me on that. It'll definitely be Friday, and I will send information out on the Google Classroom with that. Now, anyone who needs more assistance, please contact me via Google Classroom or my email address. We can always set up a private Zoom conversation. We can try to do it just typing back and forth in the classroom or on my email address. I think the Zoom would probably be a little bit easier. But just do note, I have 2 other classes going on and a child with no child care and all that stuff. So let's just not contact me all hours of the night. Alrighty. So that's about that. And, well, I'll talk to you guys soon.